So let us see if we can compute the energy density, the energy content of a field. We know that an electrostatic field stores energy. And where does this energy come from? This energy, of course, is stored in your volume in the field because work has been done to position electrostatic charges at their position. Work has been done to bring these charges from infinity and put them where they are stationary, and whatever work has been done for that has been stored in the field as potential energy. So let us see if we can evaluate how much work needs to be done to bring and position a conglomeration of charges. Let us consider a number of point charges Q1, Q2, Qn. So let's take the first point. If you have a point 1 and you want to bring charge Q1 from infinity and put it at point 1, do you need to do work? No, you do not need to do any work to bring the first charge from infinity and position it at point 1. However, when you've already put a charge at point 1. Now, if you want to position another charge at point 2, there is already a charge at position 1, and it will exert a force on any charge that you want to position at point 2. What is the amount of work that needs to be done? The amount of work that needs to be done is equal to Q2 into V21. What is V21? V21 is the potential at point 2 due to the charge at 1, which is Q1. So Q2 V21 tells me the amount of work that I need to do to position charge Q2. Now, if I want to position another charge at point 3, I will have to do more work. The total work needed to be done to position charge Q3 will be equal to Q3 V31 plus Q3 V32. V31 is the potential at point 3 due to charge Q1, and V32 is the potential at V3 due to charge Q2. The total of this is the total work that is needed to be done on charge Q3. Similarly, work to position Q4 is equal to Q4 V41 plus Q4 V42 plus Q4 V43 and so on and so forth. Now let us look at this quantity Q3 V31. Q3 V31 can be written as Q3 Q1 4 pi epsilon naught R13 by Coulomb's law, and this can now be written as taking Q1 out and taking Q3 inside, Q1 Q3 by 4 pi epsilon naught R31. R13, remember, is equal to R31. What is the advantage of writing it in this way? So therefore, this can now be written as Q1 into V13, because Q3 by 4 pi epsilon naught R31, it is the potential at point 1 due to charge at Q3. So that means the work that is needed to position a charge at point 3 against a charge which is present at point 1 is equal to the work that you would need to position a charge at point 1 if there was a charge Q3 already present at point 3. So therefore, the total positioning work is the total of all the work that is done on all the charges, which is equal to WE equal to Q2 V21 plus Q3 V31 plus Q3 V32. So work on Q3 plus Q4 V41 plus Q4 V42 plus Q4 V43 and then so on and so forth. And this is the total work which will be stored as the potential energy of the field. Now, applying this manipulation that we have just talked about, we can write WE as Q1 V12 plus Q1 V13 plus Q2 V23 plus Q1 V14 plus Q2 V24 plus Q3 V34. So what I'm essentially doing is I am replacing each potential at a point with a higher subscript with the potential at a point with a lower subscript due to the charge of the higher subscript. So V21 being replaced by V12, V31 being replaced by V13 and so on. Now these two WE, I have two equations for WE. Let me add them together. So 2WE is equal to Q1 into V12 plus V13 plus V14 plus Q2 taken out, V21 plus V23 plus V24, Q3 taken out, V31, V32, V34 and so on and so forth. I'm just clubbing all the terms with Q1 together, all the terms with Q2 together, etc. So if you now look at what you have within the brackets, V12 is potential at 1 due to charge at Q2. V13 potential at 1 due to charge Q3, V1 is potential at 1 due to charge Q4, and so on, V1 potential due to charge at N. So that means if you add these terms together, you get the total potential at point 1 V1, and the total potential at point 1 V1 is due to all the charges from 2 to N except charge Q1. So therefore, now I can write WE as half summation QMVM with M going from 1 to N when I have N number of charges. If instead of having a conglomeration of point charges, if I have a continuous volume charge distribution, I'm going to replace that summation by a volume integral. So therefore, WE can now directly be written as half volume integral of rho V dV. Now let us look at this term and see how we can evaluate this integral. Rho V by Gauss's law is equal to divergence of D. So therefore, I replace rho with divergence of D. So now my volume integral becomes half volume integral of divergence D into V. D is a vector quantity, V is a scalar quantity. Now, if you look at this term, divergence of V into D, that is the divergence of the product of a scalar and a vector, is identically equal to the divergence of the vector quantity D multiplied by the scalar quantity plus the dot products of the vector quantity and the gradient of the scalar quantity. So by applying this identity, I can write divergence of D into V as divergence of Vd minus D dot grad V. The whole thing is within a volume integral. If you do that, let us leave the second volume integral untouched, but the divergence of a vector quantity V into D can be written as the surface integral of the same vector quantity, which means the volume integral of divergence of Vd can be replaced by the surface integral of Vd dot ds. The second term, which is a volume integral, is left as it is. For the moment, let us assume that the first integral vanishes. The first term goes to 0. In which case, I am left with the second term. Grad minus grad V is equal to E, so I can replace that with E. So the volume integral now becomes half D dot E dV, and D is equal to epsilon naught E. So if you replace that, what you have is half epsilon naught E square. So the total energy that you have in the electric field is WE, which is equal to the volume integral of half epsilon naught E square dV. We know that half epsilon naught E square is the energy density of at any point within an electric volume. What happens to this first term that I said? It goes to 0. Now remember, this is a surface integral, and the surface can be anywhere. And no matter where the surface is, as long as the surface encloses the entire charge and all the flux lines, the surface integral will remain the same. So what we do is, we consider this surface to be at infinity. If the surface is at infinity, and if you assume it's a point charge that you have inside the volume, then the potential varies inversely as 1 by r. The flux density varies inversely as 1 by r square. And the surface varies directly as r square. So you have r square divided by r cube, which is 1 by r, which means this entire surface integral will go to 0 at least at the rate of, at the rate of 1 by r. Instead of point charges, if you have dipoles, it will go even faster. So if you consider that the surface is at infinity so that it encompasses the entire volume, then we can think of the entire field which contains all the energy that has been expended, and that is equal to this second term, the volume integral of half epsilon E square.